Section 1 Introduction. We're going to delve into the world of transformers, a technology initially designed for language modeling, but recently explored for vision tasks. These vision transformers have shown remarkable accuracy in various visual recognition problems, such as image classification, video classification, and object detection. However, they come with a significant drawback: their high computational cost. While typical convolutional networks, CNNs, use tens of GFLOPS per image, vision transformers often require 10 times more computation, up to hundreds of GFLOPS per image. This high computational cost becomes even more pronounced in video processing due to the large volume of data, making it challenging to deploy vision transformers on devices with limited resources or where quick response times are critical. In this paper, we introduce a method that leverages the temporal redundancy between subsequent inputs to reduce the computational cost of vision transformers when applied to video data. Temporal redundancy refers to the fact that natural videos often contain significant similarities between subsequent frames. Despite this, deep networks, including transformers, are usually computed from scratch for each frame, discarding potentially useful information from previous computations. We propose that by reusing these intermediate computations, we can improve efficiency on redundant sequences. We also recognize the need for adaptivity in vision transformers. In real-world applications, available resources can fluctuate due to various factors, such as competing processes or changes in power supply. Therefore, we aim to design models whose computational cost can be adjusted in real time. While there have been previous attempts to explore temporal redundancy and adaptivity for CNNs, these methods are generally incompatible with vision transformers due to significant architectural differences. Specifically, transformers introduce a new element, self-attention, that doesn't fit with many CNN-based methods. However, this challenge also presents an opportunity. In CNNs, it's difficult to translate improvements in sparsity, the sparsity gained by considering temporal redundancy, into concrete speedups. In contrast, the structure of transformer operations makes it easier to translate sparsity into reduced runtime. We propose Eventful Transformers, a new type of transformer that uses temporal redundancy between inputs to enable efficient, adaptive inference. The term eventful is inspired by event cameras, sensors that produce sparse outputs based on scene changes. Eventful transformers track changes over time, selectively updating the token representations and self-attention maps at each time step. Our method can be applied to existing models, generally without retraining, and is compatible with a wide range of video processing tasks. Our experiments show that eventful transformers, converted from existing state-of-the-art models, significantly reduce computational costs while largely maintaining the original model's accuracy. However, our implementation does have some limitations. While we demonstrate speedups on both the CPU and GPU, our implementation is likely suboptimal from an engineering standpoint. With additional effort to reduce overhead, we believe that the speedup ratios could be further improved. Additionally, our method does involve some unavoidable memory overheads, as reusing computation from previous time steps requires maintaining some tensors and memory. These memory overheads are relatively modest. We're excited to share our code publicly, which includes PyTorch modules for building eventful transformers. Section Summary. Vision transformers have shown impressive performance in various visual recognition tasks but suffer from high computational costs, limiting their deployment on resource-constrained devices. This paper introduces Eventful Transformers, a new class of transformers that leverage temporal redundancy in video data to reduce computational costs while maintaining accuracy. The proposed method allows for adaptive inference and can be applied to existing models without retraining, making it compatible with a wide range of video processing tasks. Section 2 Related Work. In this section, we'll discuss the related work in the field of efficient transformers, focusing on how our approach differs and complements existing methods. Several researchers have previously worked on enhancing the efficiency of transformers. A common approach is to reduce the quadratic complexity of self-attention, often through low-rank or sparse approximations. However, our work takes a different route. We focus on standard self-attention, sometimes incorporating windowing. Our method is distinct and can be used in conjunction with the aforementioned techniques. There's also been a surge of interest in improving the efficiency of vision transformers by exploiting spatial redundancy within each input. Many of these methods involve pruning or merging tokens based on their importance. A prime example is the adaptive token sampling (ATS) algorithm, which adjusts its computational cost and doesn't require retraining. Other techniques include adaptive token pooling, hierarchical pooling, learned tokenization, and progressive token sampling. Our method, however, targets temporal redundancy, making it a complementary approach to these spatial redundancy techniques. We can create a model that takes advantage of both spatial and temporal redundancy by only updating tokens that are both important and not repetitive over time. We demonstrate this in our experiments by creating a simple model that combines both types of redundancy. Another related work is the spatiotemporal token selection, STTS, which uses both spatial and temporal redundancy for video inference. However, STTS is designed for models that process an entire video as input, while our method is suitable for models that repeatedly process frames or clips. Our approach is more versatile, covering a broader range of architectures and tasks. There's also been recent work on exploiting the temporal redundancy between frames in convolutional neural networks, CNNs. While we're inspired by these methods, they can't be directly applied to vision transformers due to significant architectural differences. There's limited research on exploiting temporal redundancy between subsequent vision transformer inputs. The only previous work in this area is the spatiotemporal gated transformers, STGT, method. Our work differs from STGT in two significant ways. Firstly, STGT only considers temporal redundancy within token-level operations, not within the self-attention operator. Our method, on the other hand, speeds up all major transformer components, including self-attention. Secondly, STGT uses a lossy gating logic that can degrade accuracy on long sequences with gradual changes. We avoid this problem by using an improved, reference-based gating mechanism. There are also many methods that add adaptivity to deep CNNs. However, due to architectural differences, these methods often don't translate well to vision transformers. Some recent work on adaptive vision transformers leverages redundancy within a single input, whereas we consider redundancy between inputs. Unlike our method, these approaches generally require retraining or fine-tuning the model. Finally, there's a substantial body of work on improving the efficiency of deep networks. Some propose efficient CNN architectures, while others use reduced precision arithmetic or pruning. Our method is somewhat related to pruning. It can be seen as adaptively pruning redundant tokens at each time step. Section Summary. In this section, the authors discuss related work in the field of efficient transformers. They mention previous methods that focus on reducing the complexity of self-attention, as well as approaches that exploit spatial redundancy in vision transformers. However, their method targets temporal redundancy and is complementary to these approaches. They also highlight the limited existing research on exploiting temporal redundancy between subsequent vision transformer inputs and compare their work to the spatiotemporal gated transformers, STGT, method. Additionally, they mention that while there are existing methods for adding adaptivity to deep CNNs, these methods often do not translate well to vision transformers due to architectural differences. Finally, they mention the broader body of work on improving the efficiency of deep networks, including efficient CNN architectures, reduced precision arithmetic, and pruning, with their method being loosely connected to pruning by adaptively pruning redundant tokens. Section 3 Background: Vision Transformers. In this section, we'll break down the fundamental components of a vision transformer, a type of machine learning model that's used for image recognition tasks. We'll also define some of the terms and symbols we'll be using throughout this discussion. A vision transformer is made up of a series of transformer blocks. Each block takes in a set of n token vectors, each with d dimensions. We'll represent this as a set of vectors x in a space with n rows and d columns. Before the first transformer block gets to work, the vision transformer takes each image patch and converts it into a token vector using a linear transformation. We can also add what's called a positional embedding either before the first block or at every block. This helps the model understand where each token is in relation to the others. Now, let's talk about what happens inside a transformer block. Each block takes the input vectors x and produces output vectors z, both in the same n by d space. This is done in two steps. First, we apply a process called multi-headed self-attention to the input vectors, after normalizing them with a technique called layer normalization. We then add the original input vectors to the result. This gives us an intermediate set of vectors y. Next, we apply a two-layer, token-wise multi-layer perceptron, a type of neural network, to the vectors y, again after layer normalization. We then add the vectors y to the result to get our final output vector z. The multi-headed self-attention process is a bit complex, so let's break it down. First, we apply three linear transformations to the input vectors, after layer normalization. These transformations give us three new sets of vectors, which we'll call q, k, and versus these stand for query, key, and value, respectively. We then compute a matrix A, which represents the normalized similarity between the vectors in Q and K. This is done by taking the dot product of Q and K, dividing by the square root of D, the number of dimensions, and then applying a function called softmax to each row of the resulting matrix. The output of the multi-headed self-attention process is a weighted sum of the value vectors V, where the weights are determined by the attention matrix A. This sum is then transformed by another linear transformation. In practice, we often split the vectors Q, K, and V into H smaller sets of vectors and apply the self-attention process to each set in parallel. This is why it's called multi-headed self-attention. After this, we concatenate the results from all the heads and apply one final linear transformation. One thing to note is that standard multi-headed self-attention has a computational complexity that's proportional to the square of the number of tokens. To make this more efficient, many vision transformers use a technique called windowed attention, which limits the attention computation to local windows. We can also exchange information between windows by shifting them between blocks or by interleaving global attention. Section Summary. In this section, the authors introduce the concept of a vision transformer, which consists of a sequence of transformer blocks. Each block takes a list of token vectors as input and applies multi-headed self-attention and token-wise multi-layer perceptron operations to produce an output. The authors also discuss the use of windowed attention to reduce the computational complexity of the self-attention operation in vision transformers. Section 4. Eventful Transformers. In this section, we'll be discussing our approach to speeding up vision transformers for video recognition tasks. This is particularly useful when a transformer is used repeatedly across video frames or segments of frames, such as in video object detection or video action recognition. Our main strategy is to take advantage of temporal redundancy, which allows us to reuse computations from previous time steps. We'll first explain how we can modify transformer blocks to make them aware of temporal redundancy. Then, we'll introduce a token gating module that keeps track of temporal changes and decides which tokens need to be updated. Following that, we'll show how we can incorporate our token gating logic into a transformer block, resulting in a redundancy-aware eventful transformer block. Lastly, we'll discuss strategies for choosing which tokens to update. Let's start with token gating, a method we use to detect redundancy. We propose two modules for this purpose: token gates and token buffers. These modules help us identify and update only those tokens that have significantly changed since their last update. The gate module selects a certain number of its input tokens, m, which is less than or equal to the total number of tokens, n, to send to the next layers for recomputation. It keeps a set of reference tokens in memory, which we'll call u. This reference tensor holds the value of each token at the time it was last updated. At each time step, tokens are compared to their references, and those that differ significantly from their reference are chosen for an update. Let's denote the current input to the gate as c. At each time step, we update the gate state and determine its output using the following steps. 1. Calculate the total error, E, by subtracting C from U. 2. Apply a selection policy to the error, E. This policy returns a binary mask, M, or a list of token indices, indicating which M tokens should be updated. 3. Extract the tokens selected by the policy. We represent this as the product of C and M. In practice, we achieve this with a gather operation along the first axis of C. We'll call the gathered tokens C tilde, and the gate returns C tilde as its output. 4. Update the references for selected tokens. We represent this as U, being updated by the sum of E times M tilde and C times M. In practice, we apply a scatter operation from C tilde into U. On the first time step, the gate updates all tokens, initializing U as C and returning C tilde as C. Next, we have the buffer module. This module maintains a state tensor, B, that keeps track of the most recent known value for each of its input tokens. When it receives a new input, F, C tilde, the buffer scatters the tokens from F, C tilde into their corresponding locations in B. It then returns the updated B as its output. We pair each gate with a subsequent buffer. A simple usage pattern is as follows. The gate output, C tilde, is passed to a series of token-wise operations, F, C tilde. The resulting tensor, F, C tilde, is then passed to a buffer, which restores the full shape r to the power of n times d. Section summary. The authors propose a method to accelerate vision transformers for video recognition by incorporating temporal redundancy awareness. They introduce a token gating module that identifies tokens that have significantly changed since their last update and selects them for recomputation. This module is paired with a buffer module that maintains the most recent known value for each token, allowing for efficient updates and restoration of the full token set. Section 4.2 Building Redundancy-Aware Transformers. In this section, we'll discuss how we've developed a modified version of the transformer block that takes advantage of temporal redundancy. This is illustrated in a figure that shows our design for what we call an eventful transformer block. Our approach speeds up operations that are performed on each token, such as the multi-layer perceptron, MLP, as well as the multiplication of query key and attention value, which are part of certain equations. Let's start with operations that are performed on each token. In a transformer block, many operations are performed on each token, which means they don't involve any exchange of information between tokens. These operations include the MLP and the linear transformations in the multi-head self-attention, MSA. We can save computational resources in these operations by skipping those tokens that are not selected by a gate. Because these operations are independent for each token, this doesn't change the result of the operation for the tokens that are selected. We've illustrated this in a figure. More specifically, we place a pair of gate buffer around each sequence of operations that are performed on each token. This includes the transformation of W_QKV, the transformation of W_P, and the MLP. We add buffers before the skip connections to ensure that the tokens of the two operands that are added together are correctly aligned. The computational cost of an operation that is performed on each token is proportional to the number of tokens. A gate reduces the number of tokens from n to m, which in turn reduces the computational cost of downstream operations that are performed on each token by a factor of n(m). Next, let's consider the product of query key, denoted as b equals q, k, caret t. This is part of a certain equation. If we write out this matrix multiplication, we have b_ij equals sum underscore p, q, underscore ip, left, k, caret t, right, underscore pj. An element b_ij needs to be updated if there is a change in the i_th row of q, or if there is a change in the j_th column of k, caret t. Because of the gate that we inserted before the W_QKV transformation, only some rows of q and some columns of k, caret t have changed. Therefore, we only need to recompute a subset of the elements of b. We define ~q and ~k as the outputs of the gate before the W_QKV transformation. These contain the subset of tokens from q and k that are being updated. We've illustrated our method for sparsely updating b in a figure. The product ~q, k, caret t contains the elements of b that need to be updated due to a change in ~q. We compute ~q, k, caret t, then scatter the result row-wise into the old b. We use a similar approach for the updates induced by ~k. We compute q, ~k, caret t, and scatter the result column-wise into b. The overall cost of these updates is 2 nmd, compared to a cost of n_2d to compute b from scratch. The cost of our method is proportional to m, the number of tokens selected by the gate. We save computation when m is less than n2. However, our method for updating b involves some redundant computation. Some elements of the first scattered matrix ~q, k, caret t are also present in the second matrix q, k, caret t. These overlapping elements are computed twice. We could eliminate this redundancy and reduce the cost of our method to nmd, which is less than or equal to n_2d. This could be achieved by removing the tokens in ~q from q before computing q, k, caret t. We would then scatter the result by indexing along both axes of b. We leave this as an optimization for future implementations. Finally, let's discuss a method for updating the attention value product AV. This is part of a certain equation. If we write out this multiplication, we have AV_ij equals sum_p, A_ip v _pj. Because of the gate before the W_QKV transformation, only some rows, tokens, of v change on each time step. However, there are some updated values in every column of v. Therefore, every element of A, V, will change on each time step. This means we cannot use the same strategy that we used for B, where we only updated some of the output elements. Instead, we propose a delta-based update strategy. We define A_n and V_n as the new values for A and V, and A_delta and V_delta as the changes in A and V. On each time step, we can update A, V by adding A_n, V_delta, plus A_delta, V_n, A_delta, V_delta, to the previous result A_o, V_o. We obtain A_delta, V_delta, A_o, and V_o using delta gate modules. Delta gates are similar to the gates defined earlier, with one difference. Instead of returning ~c, a delta gate returns u and ~e, where ~e is the result of gathering the selected indices from e. U represents the effective current value of the gate's output, corresponding to A_n or V_n. ~e represents the amount of change on the current time step, corresponding to A_delta or V_delta. We've illustrated our approach for efficiently computing the three delta terms in a figure. We remove the columns of A_n that correspond to 0 rows in V_delta. These columns will always be multiplied by 0. We remove rows of V_n analogously to produce ~v_n. We then compute ~a_n, ~v_delta, plus ~a_delta, ~v_n, ~a_delta, ~v_delta, and add the result to the previous value of A, V. The product ~a_delta, ~v_delta, assumes the columns of ~a_delta are correctly aligned with the rows of ~v_delta. We achieve this alignment by forcing the A gate to select the same indices as the V gate. Using a separate policy in the A gate would be possible, but would require a realignment operation before computing ~a_delta, ~v_delta. Further, forcing alignment allows us to eliminate a multiplication by rearranging the equation as ~a_n, ~v_delta, plus ~a_delta, ~v_n, ~v_delta. This equation has a cost of 2m_d, compared to n-2d for a standard multiplication. We see savings when m is less than n2. Section summary. In this subsection, the authors propose a modified transformer block called the Eventful Transformer block that exploits temporal redundancy. They introduce a gate buffer pair around each sequence of token-wise operations to skip unnecessary computations, reducing the computational cost. They also describe methods for updating the query key product and the attention value product, achieving efficient computation and reducing redundancy. Section 4.3 Token Selection Policies. In this section, we'll be discussing the different strategies we use to select tokens for our Eventful Transformer model. This is a crucial aspect of the model's design, as it determines which tokens will be updated based on a given error tensor. One of the strategies we use is the top R policy. This method selects the R tokens with the highest error, measured using the L2 norm. This approach is simple and efficient, with only one parameter that can be easily adjusted. By changing the value of R, we can directly control the computational cost of the model. This makes the top R policy ideal for applications where computational resources are limited or fluctuating. We primarily use this policy in our experiments. Another strategy we use is the threshold policy. This method selects all tokens where the error exceeds a certain threshold. This policy is adaptive, meaning the number of tokens selected depends on the amount of change in the scene. This adaptability can potentially lead to a better balance between accuracy and computational cost. However, determining the best threshold value can be challenging, as it depends on the distribution of token vectors, which can vary across layers. Additionally, this policy doesn't provide a fixed computational cost. Therefore, it's better suited for applications with more flexible resources, where achieving the best possible balance between accuracy and cost is crucial. We also consider other, more sophisticated token selection policies that could potentially improve the balance between accuracy and cost. For instance, we could use a learned policy, such as a lightweight policy network. However, training the decision-making mechanism of the policy could be challenging due to the binary nature of the mask. Another idea is to use an importance score to inform the selection. We're leaving these ideas for future exploration. Next, we'll discuss our experiments and results. We tested our method on video object detection and video action recognition tasks. We used the ILS-VRC 2015 ImageNet Vid dataset for video object detection. The dataset contains 555 videos with lengths of up to 2,895 frames. We evaluated the mean average precision (MAP) metric with an intersection over union (IOU) threshold of 0.5. We used the VT-DET model, which we applied to individual frames of an input video. The model combines a plain transformer backbone with a standard detection head. The backbone consists of 12 blocks with interleaved global and windowed self-attention. Token vectors are 768-dimensional. Self-attention operators have 12 heads and employ learned relative position embeddings. The model maps each 16 by 16 image patch to a token vector using a linear transform. We converted the model to an eventful transformer following the method described earlier. We fine-tuned the original VT-DET weights for vid object detection. We trained and evaluated at a resolution of 1024 by 1024. To understand the effect of token count, we also evaluated at a resolution of 672 by 672. We compared our method against a version of the STGT method. We also evaluated an ablated version of our approach that only accelerates token-wise operations. Our results showed that our method significantly reduces computational cost with only minor reductions in accuracy. For example, at a size of 1024 with R equals 768, our approach reduced the cost from 467.4 GFLOPS to 122.3 GFLOPS, 3.8x lower, while reducing the MAP 50 score from 82.93 to 81.25. minus 1.68% in absolute MAP 50. At a size of 672 with R equals 384, we reduced the cost by 3.7x with a minus 0.85% change in MAP 50. In conclusion, our approach provides a significant improvement in the balance between accuracy and computational cost compared to the STGT method. Adding redundancy awareness to the query key and attention value products further reduces the cost, especially at low R values. Section Summary. Token selection policies are an important aspect of the eventful transformer design. The top R policy selects the R tokens with the highest error norm, providing control over computation cost. On the other hand, the threshold policy selects tokens based on a threshold value, making it input adaptive but difficult to determine the best threshold. More sophisticated policies, such as learned policies or importance scores, could be explored in future work. Section 5.2 Video Action Recognition. In this section, we're discussing our approach to video action recognition, specifically focusing on verb classification. We've tested our method using the Epic Kitchens 100 dataset, which is a collection of dynamic first-person perspective videos annotated with 97 verb and 300 noun classes. The training and validation sets contain 67,217 and 9,668 action instances, respectively. Our model, Vivid, is based on VIT-B and uses separate spatial and temporal submodels. The spatial submodel, which requires the most computational resources, is applied sequentially to 16 clips, each containing 2 frames. The outputs from the spatial model are then combined and passed to the temporal model, which provides a class prediction. This prediction is an average taken from 12 video views, each view being a 320 by 320 by 32 shape. Each of these views is divided into 4 temporal views and 3 spatial crops. Unlike VT-DET, Vivid includes a class embedding token, doesn't use windowed self-attention, and doesn't use relative position embeddings. We've modified the spatial model to become an eventful transformer. However, this naive replacement led to a significant drop in accuracy, around 10% with R equals 100. We believe this is due to a shift in the distribution of inputs to the temporal model. We managed to regain most of the lost accuracy by fine-tuning the non-eventful temporal model using the outputs from a frozen eventful spatial model. Our experiment protocol involved starting with a Vivid model pre-trained on the Epic Kitchens 100 dataset and fine-tuning the temporal model as described above. We fine-tuned different model variants with policy R values of 50, 100, and 200, out of a maximum of 401 tokens. We used the top 1 accuracy metric to report our results, as per standard protocol. Our results showed that the Eventful Vivid model performed well across a range of R values for each of the fine-tuned variants. We tested the original fine-tuned R value, as well as 20% and 40% above and below this value. We found that we could achieve significant computational savings with only a moderate reduction in accuracy. For instance, with R equals 140, we reduced the computational cost by 2.4 times while only reducing the accuracy by 1.62%. Furthermore, the model maintained its adaptability even when fine-tuned with a single R value, demonstrating a favorable accuracy compute trade-off across a range of R values. Section Summary. In this section, the authors evaluate their method for action recognition using the Epic Kitchens 100 dataset, which contains egocentric videos annotated with verb and noun classes. They use the Vivid model with factorized spatial and temporal submodels and fine-tune the temporal model on the outputs of a frozen spatial model to recover lost accuracy. The results show that by adjusting the policy R values, they achieve computation savings with only moderate reductions in accuracy, demonstrating an adaptable and efficient model. Section 5.3 Spatial Redundancy and Runtime. In this section, we'll be discussing the concept of spatial redundancy and its impact on runtime. We'll also be conducting a simple experiment to illustrate this concept in the context of Eventful Transformers. Eventful Transformers are designed to take advantage of temporal redundancy, which is a feature that sets them apart from previous models that primarily focused on spatial redundancy. In this experiment, we're going to explore how spatial redundancy can be utilized in Eventful Transformers. To do this, we're going to use a modified version of a method that applies spatial pooling to the self-attention key and value tokens. We'll apply this method, using a 2x2 pooling, to the global self-attention operators in the VT-det model. We'll then evaluate this method, both with and without the awareness of temporal redundancy. In the model that is aware of temporal redundancy, we pool the key and value tokens after they've been buffered. We pool the modified key token by first pooling the active indices, which is the same as max pooling the mask, and then gathering the buffered key tokens using the pooled indices. Our results, which are shown in a table, are for a resolution of 1024. Additional results for a resolution of 672 can be found in the supplementary material. What we found is that the spatial and temporal methods complement each other, both contributing significantly to reducing the computational cost. We'll discuss spatial redundancy methods in more detail in a later section. Next, we'll look at some preliminary runtime results. These were obtained on a CPU, Xeon Silver 4214, 2.2 GHz, and a GPU, NVIDIA RTX 3090. The details of the experiment can be found in the supplementary material. Our results, which are shown in a table, indicate that adding awareness of temporal redundancy can lead to speed increases of up to 1.74 times on the GPU and 2.48 times on the CPU. However, these results should be viewed as a proof of concept. We believe that with further engineering effort, such as replacing standard PyTorch operators with custom kernels or using a high-performance inference framework, these speed increases could be improved. Finally, we'll look at a visualization of updates. We have an example video sequence that shows the model predictions, at the top, the token-wise L2 norm of the error, in the middle, and the update mask, at the bottom. What we found is that larger error values correspond to dynamic regions in the image.